Hello, my name is Taku Nishino, and I'm from the Institute of Science Tokyo. So today I will present about stability analysis of persistence based on the passivity. So let's start. So let me start with a brief self introductions. I'm currently a doctoral student at the Institute of Science Tokyo, and I've been at the university since my undergraduate studies, mainly specialized in system and control engineering. So this field involves modeling various real-world systems as differential equation, and then perform stability analysis and controller design, and so on. So in my case, I apply this to power systems. And in my free time, I enjoy anything that gets me moving. Last year, I tried to mountain climbing and even learn marathons. And I also developed dynamic simulation using MATLAB as part of my research. Currently, I'm working at a MATLAB assistant at my universities. So let's dive into our main topics. So first, I will discuss persistent stabilities. So there are various types of stability in power systems, such as a voltage stability and frequency stability. So in this research, we focus on the transient stability of power systems, which refer to the ability of the system to maintain its operating point following the disturbance. This is closely related to what is often called angular stabilities. So to begin with, let's start with a simple example of system simulation. In this simulation, we analyze a modeling consisting of three generators and consider the case of fault in this power system. The response of frequency deviation and voltage in each generator are shown in the graph. These parameters oscillate temporarily, but gradually converge to their initial values. So however, for the same model and operating point, the result seems to diverge when the disturbance due to the ground fault increase. Uh, so, furthermore, for the same fault disturbance, it seems to destabilize if this system is operated with different values. Per system may or may not be unstable depending on a variable of conditions. So why does this happen? The answer is the per system are nonlinear system. So to understand this, let me explain using an image. So when discussing a system stability, two types are to be considered. First is steady state stability, and the second is the transient stabilities. So um, steady state stability refers to the ability of a per system to so, return to equilibrium after a small disturbance caused by a gradual change in power supply and demand. So on the other hand, transient stability refer to the system's ability to resume a synchronous state after a large disturbance. So, so sorry, transient stability, on the other hand, refer to the system's ability to regain a synchronous state after a large disturbance. Even if the system exhibits steady state stability at an equilibrium point, a significant disturbance can still cause instability. So this concept is illustrated in the image. On the left side, a disturbance adds kinetic energy to the lead ball. Despite this energy, the ball remains within the two peaks. So like this. Uh, sorry. So uh, the red box represents the range within which a given energy function can return to equilibrium. So this range is known as the domain of attraction. So this research focuses on estimating the size of this domain of attraction within the persystem's energy functions. So next, we are model the persystems. So this study considered analysis of persystems consisting of only synchronous generators. A persystem consists of two main parts, models representing individual components and a transmission network connecting them. So let's begin by discussing the transmissions network. So the persystems in this study uses phasor value for voltage and current. So therefore, the transmission network can be represented as an algebraic equations. When we consider the point where each device connects to the system as buses, the current flowing from each device is uniquely determined if the voltage at each bus is determined. And the next is the synchronous generator models. The differential equation of the synchronous generators can be represented as this. Delta represents the rotor angle, and omega is the frequency deviation, and E is the internal voltage. And as a connection term with the persystem, we represented it as an algebraic equation like this. So by combining these generator output equation and network equations, we obtain an algebraic equation like this. In other words, the power system is modeled as a set of differential algebraic equations. So for example, if we have three generators, we end up with three differential equations. And by combining the generator's output equations and network equations is equal. So this is algebraic equations. Yes. So next, we are going to the passivity analysis of power systems. So the synchronous generator model represented as like this, and we now divided two subsystems. One is the swing equations, and the other is the electronic dynamics. So the first and third equation of the synchronous model can be considered as electronic dynamics, and second is the swing dynamics. So if there is three generators in the power systems, we can consider the two parts of the subsystem, and the whole power system is modeled as a negative feedback of swing dynamics and electromagnetic subsystems. Yeah. And now we call the swing dynamic subsystem is subsystem F. The electromagnetic subsystem is called as subsystem G. And subsystem F is always passive because the M and D always positives. So if the subsystem G is passive, the whole persystem is asymptotically stable. Now we discussed the equilibrium, the concept called equilibrium independent passivities. If the system sigma is represented as this, and sigma is EI passive if there exists a positive definite function satisfying following equations. So, and the storage function of EI passive system can be expressed in terms of the Bregman divergence of potential energy functions. In the existing research, the storage function of subsystem F can be represented as like this. And the energy function of subsystem G can be represented as this. So when the subsystem G is passive, the storage function can be expressed as like this. Sorry. So in the image, the subsystem F is interpretable as rotational energies. And on the other hand, subsystem G can be interpretable as potential energy. So each subsystem is passive. The negative feedback is the symptotically stable. But in the persistence, the shape of the shape of the potential energy function can be can't be get even because it is nonlinear system. So in this research, we want to estimate the shape of the energy functions. The important thing is that the storage function is expressed in the form of the Bregman divergence. So if the energy function gets like this, and the equilibrium point set to this point, the Bregman divergence can be get by the shift of the energy functions. The most important point characteristic is the storage function has the following equations. The storage function has at the equilibrium point, this function gets to 0, and the gradient is also to 0. And the Hessian of the storage function equals to the Hessian of energy functions. So the third equation is most important. The storage function depends on where the equilibrium point is to set, but the Hessian of storage function is not don't depend on the equilibrium point because these equations. So we can estimate the shape of storage function from the region in which the energy function is convex. So for example, the Hessian of energy function is convex area gets to the blue areas, and the equilibrium point move to this around this. The storage function gets to the black line, So if the equilibrium point is located near to the bound of convex areas, the domain of attraction is very small, but on the other hand, the equilibrium point is set to the center, the near center of convex area. The domain of attraction is largest. So we evaluate these considerations by numerical analysis. So in this analysis, the 3-bus model shown in the slide is used. The color map shows the region where the potential energy function is convex. The Hessian of the potential energy function is obtained, and the multiple of its eigenvalue are used as indicator for the color map. These equilibrium points are selected for this system, and simulation are performed for each case. The plane is divided into the 100 and 100 mesh, and the points in each grid are set to the initial value. The purple area indicates the points that converge to the equilibrium points due to the numerical simulations. So the research confirmed that if the equilibrium point is placed near the center of the convex regions, the domain of attraction becomes larger. This confirms the theoretical considerations. So to confirm this correlation, we create a scatter plot. The graph on the left uses the sum of the Hessian eigenvalue on the horizontal axis and the size of the domain of attraction on the vertical axis. The right graph uses the product of Hessian on the horizontal axis. So to illustrate this point, the equilibrium point is taken as the green point in this graph. The multiple of the Hessian eigenvalue is 0.65 for the index of the color map and 2444 grid point in the purple area. For this equilibrium point, the horizontal axis corresponding to the 0.6 and the vertical axis corresponding to 2444. So this scatter shows the result of this same analysis for 100 equilibrium points. The result shows a positive correlation between the size of the Hessian and the domain of attraction. This suggests that, for example, when focusing on the sum of eigenvalue, the magnitude of the domain of attraction can be compared by the place of the Hessian of potential energy functions. So far, I've discussed the passivity-based analysis of the domain of attraction in Earth systems. And next, I would like to explain a method for visually understanding the dynamic behavior of Earth systems. So the phasor values are commonly used to analyze power systems. The value of an AC power source at each point in time can be mapped to a point of complex planes. So several techniques already exist for analyzing voltage value as vector or complex numbers. So using this approach, we map the terminal voltage of each generators and the bus voltage to point on the complex plane. And next, let's consider the dynamics of synchronous generators. So we transform the synchronous generator model shown easier into this form. The first term is the differential of the differential equation is the corresponding to the feedback term for the on states, and second is the interaction term with the network, and the third term is external inputs. So the red and blue term is corresponding to the distance of this map. So V absolution of V and sine delta minus angle V is like this and so on. So in other words, if we imagine spring between the nodes representing the buses and the generators, the term highlighted in blue and red can be understood as the elastic force of the spring. The other term can also be interpreted as damping or elastic terms. So, therefore, when considering the entire system, it looks like this. In essence, the power system can be understood as a network of spring and dampers. A key differential form of vector method mentioned previous. A key which involves static analysis. Is the model is the like the sorry. Its model can be dynamic analysis geometrically represent the interaction between all nodes in the systems. So let's use the visualization technique to observe the response of persistence. Initially, each component rests at maintains at equilibrium points determined by the external input values. And imagine the line connecting each node as a spring with an elastic force. So now let's observe the system's response when a ground fault occurs at a specific path. So when a ground fault occurs, the voltage at a particular bus temporarily drops to zero. After the fault clears, the power system attempts to return to its original states. Due to the state transition during the fault, a pulling force acts on each node, like spring pulling them back to their original positions. The animation shows the system oscillating and eventually returning to a steady state. So on the other hand, let's consider a scenario with a larger disturbance. If a significant disturbance occurs, the angle between the node becomes too large and restoring force are lost. This situation can be visually understood through animation on the slide. So the advantage of this visualization method is its compatibility with the energy function used in the passivity analysis discusses in the previous terms. By transforming the energy function like this, each term can be interpreted as the sum of spring elastic potential energies. In essence, the energy function of the persistent subsystem G corresponding to the elastic energy stored in the spring in these models. So this provides a direct visuality representing of the system's energy landscapes. So in the passivity terms, we divided the two subsystem. Subsystem F is the swing dynamics, and subsystem G is electromagnetic subsystem dynamics. So each energy function of the subsystems corresponding to the rotation energy and strain energy of springs. So the Bregman divergence means that easy samples like this. So we understand the Bregman divergence of subsystem G of energy function of subsystem G can be understood like this. And third point, the stability treated in the power field, power field can also be viewed geometrically. The voltage stabilities means that keep plus minus 6 volt from standard voltages, and the frequency stability can be understood the keeping frequency division within plus minus 0.2 Hz and maintaining system stability can also understand like this. So, okay, so that is all. Thank you.